Have you ever really thought about the hidden world of molecules that's all around us? I mean, it's in the sharp tang of vinegar, the sting of an ant bite, even in butter. Well, it turns out they're all connected by one fundamental family of organic compounds. So today, let's dive into this world and really get to know the identity of carboxylic acids.
Now, to truly get what makes these molecules tick, we kind of need to master two different things. Think of it like this. First, we're going to learn their language, which is all about how we name them. Then, we'll dig into their anatomy, the actual physical and electronic structure that gives them all their unique properties.
All right, let's kick things off with the language. Way before we had some universal system, the early chemists basically just named things based on where they found them. It's kind of like a chemical dialect.
And it's actually pretty cool how intuitive these old names were. They really tell a story of discovery. The acid that was first found in ants, they called it formic acid, from the Latin word for ant, formica. The sour stuff in vinegar, that's acetic acid, from acetum. And the compound that gives old butter its unique smell, butyric acid, from the Latin word for butter, butyrum. All these common names ending in iic acid have a history.
But, while those stories are really fascinating, they can get confusing pretty fast. For clear scientific communication, chemists needed a universal syntax. And that's where the IUPAC system comes in.
The beautiful thing about the IUPAC system is just how logical it is. The rule is super simple. You find the longest carbon chain that has the carboxyl group, you take the name of that alkane, like methane or ethane, you drop the final E, and you just stick oic acid on the end. Now, here's the most important part. The carbon in that carboxyl group is always carbon 1. That's your starting line, no exceptions.
Okay, let's see how this works. Our old friend formic acid, with its one carbon, comes from the alkane methane, so it becomes methanoic acid. Acetic acid has two carbons, so it comes from ethane, making it ethanoic acid. You can see the pattern, right? Propionic acid becomes propanoic acid, and butyric acid becomes butanoic acid. It's a clean, logical system.
Simple enough for a straight line of carbons, right? But what happens when things get a little more complicated? What if a molecule has two carboxyl groups, or even three? Well, the system just adapts with a few really smart tweaks. First, you keep the full alkane name. This time, you don't drop the E. Second, you add a prefix, like di for 2 or tri for 3, right before the oic acid part. And third, you just use numbers to show exactly where those groups are on the carbon chain.
Let's look at some examples. A two-carbon chain with two carboxyl groups isn't just ethanoic acid, it's ethandioic acid. See, we kept the full ethane name. And that same logic just keeps going for propane dioic, butane dioic, and so on. Now check out that molecule on the bottom with three groups. Its name is propane 1,2,3-tricarboxylic acid. It tells you everything you need to know.
And this system isn't just for chains. It works for aromatic rings, too. The simplest one is benzoic acid, but its proper IUPAC name is benzene carboxylic acid. If you've got two groups, like in phthalic acid, you just number their spots on the ring, benzene 1,2-dicarboxylic acid. The logic just keeps on working.
Okay, so I think we have a pretty good handle on the language now. We can read the names, we can write the names, but why do these molecules act the way they do? Well, to answer that, we've got to go deeper than just the names. We have to look at their anatomy.
Let's start with the basic architecture. The actual shape of the carboxyl group is the foundation for pretty much all of its chemical behavior.
Let's zoom in on the geometry here. That central carboxyl carbon and the three atoms it's bonded to, the two oxygens, and whatever else is attached, are all perfectly flat. They lie in the exact same plane, and the bonds that separate them are all spread out at about 120 degrees from each other. So this isn't some floppy, flexible group. It's a very specific, locked-in planar structure.
But there's more to anatomy than just the bones, right? We have to look at the electrons, because that's where all the action happens. And this brings us to a really important idea, resonance.
You see, the electrons in this group aren't just sitting still. A pair of electrons from the OH group can actually jump over to form a double bond with the carbon, which then pushes the electrons from the original double bond up onto the other oxygen. The real molecule isn't one or the other, it's a hybrid of these forms. This sharing of electrons across that whole three-atom system is called delocalization, and believe me, it is a huge deal.
So why do we care about all this electron sharing? Well, let's compare our carboxyl group to something similar, a ketone. Over on the left, a ketone's carbon-oxygen double bond makes that carbon really electron poor,
or what we call highly electrophilic. It's just begging to be attacked by other molecules. But now look to the right at our carboxyl group. That resonance we just talked about spreads out the charge. The other oxygen helps share the load. And what's the result? The carboxyl carbon is way less electrophilic, and so it's much less reactive than a ketone's carbon. The anatomy directly controls the function.
So, let's bring it all home. We've looked at the language of how we name these things and the anatomy of how they're built. What are the absolute key points you need to remember?
Here are the big ones. First, for the IUPAC naming, just swap the alkane E for oic acid. Easy. Next, and don't forget this, the carboxyl carbon is always your starting point, always carbon 1. Structurally, remember that the whole group is flat, with those 120-degree bond angles. And finally, the electronics. That resonance spreads out the charge, making the central carbon less reactive than you might think.
And when you put the language and the anatomy together, you really unlock the ability to read chemistry. A molecule like 2,4,6-trinitrobenzoic acid might look super intimidating at first, but now you've got the tools to decode it. You can see the parent name, you know where all the groups are, and you understand the fundamental properties of that carboxyl group at its heart.
You know, once you learn the rules of the language and the anatomy, what looks complicated just becomes a story that you can read. It really makes you wonder, doesn't it? What other molecular stories are all around us, just hiding in plain sight?